Alright, welcome back to another video here, this channel. Today I'm going to talk to you about this paper called Classical Planning in Deep Latent Space, Bridging the Subsymbolic-Symbolic Boundary. Okay, let's talk a little bit first about the motivation. So in classical planning, you usually have a symbolic representation of your domain and your current problem state. And these are usually provided by a human, so-called knowledge engineering. And because this requires a human to input the knowledge, the knowledge acquisition bottleneck arises. And deep learning is good at producing sub-symbolic continuous representations from observations, but these sub-symbolic representations can't be used directly by planners. So in this paper, they asked the question, can we combine these two? And so can we learn symbolic representations from image observation in an unsupervised manner? And can we then use these symbolic states to perform planning? And so let's get into the method. This is kind of a messy image, but we'll go through each individual part of this one. I think the most important parts are the state autoencoder, the action model, and then the plan is just a regular planner, but we'll go through each of these and hopefully by the end of the video you will understand this picture. So what is the state autoencoder? And if you don't know autoencoders, there's a bunch of good content about these on YouTube. I will link to some videos in the description, but basically what it is, it takes an image as the input and it encodes this to some kind of latent space, and then a decoder reproduces the input image. And in a normal autoencoder, the latent space is a continuous representation, but here they want to have a discrete representation, so they use something called a Gumbel softmax. And I won't go into detail on this here, but I'll put some links in the description for this one. And this is kind of how it looks. So you have an image, you have a neural net, produces a latent representation, and then the decoder produces the image again. And then you have the action model acquisition, which was the second part there, presented the image. And they proposed two different methods for using for acquiring the actions. So not only do you want to parse your state symbolically, but you also want to know what actions are available in this domain. And first they learn state representations and then use these representations to infer what kind of actions there is and how they change the states. And the second one learns the actual representations directly from observations. So in the first case, we're given two images and assume that between these images an action was performed. So first we map these into Boolean vectors, both images, and then these Boolean vectors can be considered your the predicates that are true in the states. So 0 would mean this predicate is false. 1 would mean that the predicate is true. And then what they do is they say, okay, so we have this first symbolic state. All of these predicates that are true in the states are taken as preconditions. And then for the add delete effects, they look at, okay, which predicates changed from the first to the second state. And if the predicate went from being false and then true, that would mean an add effect. And if the opposites were the case, then that would be a delete effect. So here is an example of a Boolean vector that is mapped to these symbolic predicates. So there is some problem with this approach. For example, it needs the whole state space as the input. It cannot generalize at all from a small portion of the state space, which we kind of want to do. And it's also another limitation that all predicates in the initial state are not necessarily required as preconditions. So if you're familiar with the blocks world, this example will make sense to you, but there is one action where you can pick up a block, and in order for this action to be applicable, the preconditions are that this block needs to be clear and that there's not a block in the hand. And if we have a state where there's the block A is on top of block B, then this action model acquisition method would say that, okay, on A, B needs to be true in this state for this action to be applicable, but that would be an incorrect inference, as we know from the blocks world. So they propose another method for acquiring the actions, which comprises of two components. So we have the action autoencoder and the action discriminator, and I'll go through these in detail. And here is an image of the action autoencoder. So basically it takes two symbolic bit vectors, which represents two different states. It gives these to a neural network, and the neural network predicts the action that was applied to go from the first to the second state. And then the second network here tries to generate the second state based on the initial state and the action taken. So we'll go through this a bit more in detail. So yeah, as I said, two neural networks. One predicts the action, the other one applies the action and predicts the state. And these S and T states come from the state autoencoder previously mentioned. And the difference between this action autoencoder is that it works with symbolic states instead of images. And then we have the action discriminator. So it looks at two states and says, is there an applicable action between these states? So can you go from state S to state T, basically, given some action, one action? And so it learns to discriminate between valid actions from invalid ones. And it's a binary classification, basically saying there is an action you can go from S to T, or there is not. But the problem here is we only have, in the observed data, we only have transitions that are correct, so we don't have any negative examples. And the way in the paper they try to solve this problem is they generate a mixed examples data set. And what is meant by mixed examples is that they look at all the different transitions. So we take S and S as the initial state, apply all the different actions to this state. And because not all actions are applicable in this state, we will get some false examples, but we don't really know which ones are true or not. We only know that there are some positive examples here. For example, for the actions that are applicable in state S, that would be a true case. And we remove those because we already know that they're true. So we want to increase the number of potentially incorrect examples here. So just to summarize, they propose this LatPlan, which is planning in latent space. Their purpose is to be able to just look at images, get whatever domain representations, whatever domain represent these observations, and then be able to do planning with these representations. And they use the Gumbel softmax to create symbolic representations. And yeah. And now for the discussion part. So there are a few problems with this approach, I'll say. The first one is that the symbolic representations they get are optimized to recreate the original image, but that is not necessarily the best representation to do planning. So for example, you can have two different images that will produce the same symbolic state, so the same latent representation, but when you use the same latent representation in the decoder, you will get the same image. So which one of these are correct? And humans aren't really able to, we're able to parse our environment symbolically, but we're not really able to go from the symbols to recreate the environment. Not exactly as it was when we observed it. And another limitation is that all the predicates from the initial state are taken as the preconditions for the action, which means that we will have a lot of different actions, but in other planning domains we usually have a few actions, and the actions are combinatorial. And also this brings us to the last point here. And here all the symbols are independent from each other. You can see them as orthogonal in the latent space. But if we again go to blocks world as an example, we can have two predicates that are clear A and clear B. And this clear, we have like this lifted predicate, right? The clear X, where X is a variable, can take any object. And essentially, clear A and clear B would be more similar than hand empty. But in our latent space, there's no way to see this. And also the predicates are not combinatorial, which is another problem, which means they kind of blow up depending on the size of the problem. You need more and more predicates. And here is the reference to the Gumbel softmax, if you're interested in reading that. And thanks. If you have any questions or comments, just post them down in the comment section below. I'll be happy to answer those, and see you next time.